As you said, I'm Peter McGuinness. It's nice to see you all here. Are you all familiar with Imagination Technologies, or do I have to tell you who we are? She says no, he says no. Okay, we're an IP design company, very, very like ARM. I hope you can hear me. This sounds like it's cutting in and out a bit. Tell me if it's not good. It's okay. Okay. So we do high value IP, GPUs, CPUs, video and vision processing IPs, things that come with a lot of infrastructure requirements, things that come with a lot of software requirements, and a lot of not just SoC but system integration requirements. So the model that we operate on is not kind of a fire and forget sort of thing where you put IP in the library and then just let people pick it up and basically you can handle with a book of instructions how to integrate it. It really needs a kind of a collaborative approach to designing this stuff into the SoC. What that means is that as well as being an IP company, we're really a system integration company. We really need to know the entire system before we can even begin on the process of designing a piece of IP. And that's the case with the vision IP that I'm going to talk about today. We started off to look at one of the blocks on the SoC, and it's the camera block. It's a camera pipeline. It has a name that everyone's familiar with, ISP, and it has a set of functions that everyone's familiar with, which is, you take raw image data from the sensor, CMOS sensor usually, and you manipulate it to fix certain defects in the sensors. You manipulate it to correct for certain defects in the CMOS process. You correct for the lens. In general, you put in hardware and pieces of software to produce a good image. It's producing a pretty picture or a nice video. That's been the classical role of the ISP in the system. But that's changing a lot under the influence of several factors, and is moving away from just producing images and moving much more towards being a vision subsystem. So that's the theme. That's why we're saying, moving from video to vision. That's the trend in the industry. And I'll get in a little bit to where that comes from and what it means and the kinds of things that we're doing to take account of that. I'm going to pause now to learn how to use the clicker. I always get it wrong. Okay. I was expecting another slide to start with, but that's okay. I can start with this. Okay, so the uses that people are putting imaging devices to are changing rapidly. They're not just producing pictures. And let me see if I've got some sort of a pointer in here. Yes, I have. So we have here the markets that imaging devices are being used in. Set-top box. This is a new one. I mean, the television or the set-top box can now see you. That's quite a change, and it gives you an opportunity for a new user interface. Automotive is a huge one. Hang on. No. I'll try hard not to press the wrong button next time. It's the green one. Okay. So in automotive, that's a huge opportunity for vision-based systems. From everything from automatic driver assistance to security. Cameras in cars already have been used as the reversing aid. But they're being used more and more for things like collision avoidance, lane exit avoidance, other things, recognizing the environment around street sign recognition, that sort of thing. There's an enormous opportunity in automotive for extremely sophisticated vision processing. In retail, I'll give a couple of examples later on, but in retail is very, very interesting uses of cameras where a kiosk setup can actually detect who has entered into its field of vision. They can detect who you are and take certain actions based on that. And I won't go through all of these, but the point is that the workloads here are things like skeleton recognition, histogramming, lane marking detection, edge detection. These are not video or image production functions. These are computer vision, robotic vision functions. There's a fundamental shift in the role of the camera in these systems, and they're enabling all of these use cases. And the dominant characteristic of these workloads is that it has data parallelism. So that means you can take that workload and you can distribute it in the system. It doesn't have to be run on the CPU. In fact, it's more beneficial to run it on a parallel system than to try to run it on a very high frequency CPU, because you've got a better result. And by a better result, I don't just mean you get better performance, because you can. Sometimes you get worse performance depending on the characteristics of the workload, but you can get better power performance. And that's the critical thing, especially in a power-constrained SoC. Even in automotive and things like retail analytics, you still want to have a power-efficient solution, because that drives cost as much as anything else. System cost, not just SoC cost. Okay? And so these are the components that you have in an SoC. And the point that I'm making here is that if you look at the algorithms, if you look at the workloads that you build up in vision systems, they're naturally heterogeneous. And by heterogeneous, what I mean is that you can split up the workload. You can perform some of it on the CPU. You would always want to leave your control code on the CPU, because it's branchy, it's decision taking, it's essentially linear and single-threaded. But what you do want to do is you want to take the more low-level, the sort of the bulk operations, and put them onto something which is more appropriate for that kind of operation. And as I pointed out in the last slide, the vision workloads are highly parallel, and they're highly structured in the sense that you can map them onto a GPU, and a GPU is a very parallel machine. Typically, what you'll find in your average GPUs, you'll find a lot of DSPs. They may be vectorized DSPs, SIMD may be 4 wide, or it may be much, much wider than that. You get SIMD machines which are up to 128 wide, split into groups of perhaps 16. Which means that you've got an enormous amount of parallelism, as long as you've got a lot of operations that require the same instructions to be run at the same time on consistent sets of data. And that's what you've actually got when you've got a vision application. So you have the blocks, you have the ISP, the GPU, and the CPU in the system, so you have the opportunity to distribute your algorithms across all those 3 sets of resources in the system to get the best result. But this is not a static thing. There's a migration. There's likely to be a migration of functions from certain of these compute elements to others as the algorithms mature and as the standards mature. I think I've got a slide on that in a moment. So this is what a camera system looks like. This is kind of the usual camera subsystem that you would find in an SoC today. So you have this is the sensor chip. It has the CMOS sensor on there, and very often inside the same package, not on the same die, but stack in package, you'll have an imaging pipeline. And the purpose of that imaging pipeline is the old style, producing a pretty picture. The output of that is YUV data, which is then sent across to an application processor or some other processing element to take further action. About all you can do with that YUV data is you can do things like autofocus, white balance, and things like that, because you can still measure those characteristics. But you've really removed a lot of the information or lost the opportunity to produce information on the raw data, which is usable in a vision system. So what you're seeing is that an integrated vision system, this is now the SoC, and the input here is raw data directly from the CMOS sensor. So we've got rid of this SIP imaging pipeline on the sensor. We're taking in, instead of YUV data, taking in raw data, and this is the ISP pipeline. And these blocks in here are really the traditional camera IP blocks. There's the demosaicing, there's the bad pixel fixing, there's the tone mapping, there's the correction for the lens distortion, all of those things which are really very, very standard for an imaging pipeline. But they're augmented with these blocks here, where there are now elements there that are producing statistics which can be used by other compute elements in the SoC system. These elements are either the GPU or the CPU. And so you've got things like focus statistics. It's got 3A statistics. That's autofocus, auto white balance, auto exposure. And they're not being handled in the IP itself, in the image processor itself. They're actually being sent across to usually system memory, where they can be picked up either by the CPU So something like autofocus will be a CPU type of operation. It's not much data to be operated on. Auto white balance, you might want to delegate that to the GPU because there's a lot of image data to be worked on. But one of the points of these statistics is that you've already extracted a lot of the information that you need in order to perform those operations quickly and efficiently on either the CPU or the GPU. But already what you can see is that the ISP is now collaborating with the other compute resources which are on the SoC, and that changes the nature of the game. It means that you can do custom things in software on the CPU or the GPU that you didn't have the opportunity to do earlier when the imager was on a separate chip and you were just presented with a finished image. And that concept can be carried forward into other functions. Let's see if I've got a slide on that. Yeah, this is just a bigger picture of that block diagram. So over here, you can see that on the CPU, you've got a number of functions which are being performed, and then between the CPU and the GPU, you have these functions here. Now, with these functions, you're starting to get into two areas of operation which are substantially different from the traditional camera pipeline. The first one is computational photography. And computational photography covers a number of subjects. The simplest and the most direct is things like high dynamic range photography, where you take a number of different images and you can interpolate between those images on a per pixel basis to produce from the two differently exposed images, you can produce a single image which has better exposure characteristics across the dark areas to the light areas. It's called high dynamic range. You don't actually have a greater dynamic range, but what you have done is you've done on a per pixel basis, you've allocated the available dynamic range more appropriately for that image, so you get a better exposure. It's a multi-exposure image is what you're getting in the end. But the result is actually familiar to people who have used cell phones that have that functionality, and it does produce a better image. One of the other aspects of computational photography are that we now have systems coming along which are using multiple cameras or multiple arrays of cameras on a wafer scale. So you'll have sensors which have got multiple lenses in front of them, which give you a different parallax viewpoint of the scene that you're looking at. And there's a number of things you can do with those things. You can take a photograph with a very wide depth of field, very deep depth of field. So it's as though it has a very small aperture. But you can take that with a lot of light getting into the camera, so you get that benefit. And then you can go back after the fact, and then you can re-establish the depth of field. So you can bring the focal point forward or move it backwards, narrow the depth of field. And so essentially you can create the picture after you've taken the image. You've taken a raw image that needs to be processed. And there's a lot of companies out there who are building cameras, in fact, based on this principle. But then there's other things here. We've got these things are now moving towards computer vision, towards robotic vision. So face detection, rolling shutter is a basic sort of camera. That's just something you need to correct for the fact that CMOS sensors need to be cheap and they don't have a mechanical shutter. But you can do that on the CPU, save some cost over in the sensor end. Face detection is moving on towards the robotic vision side of things, and that's where it really starts to get interesting, because that's where you start to enable completely new algorithms and completely new markets using the image sensor. So a few comments on the types of things you want to do on the CPU and the types of things you want to do on the GPU. I don't need to spend a lot of time on this. CPUs are very good, even multi-core CPUs are good at doing certain kinds of operations. And what it basically boils down to is that, single-threaded or very low numbers of threads, non-parallel serial code, which has a lot of branching. The CPUs put a lot of effort into being able to branch and lose, a little performance, but not much. They're very, very good at that, and so they can do things with very low latency, but you need small amounts of data to work on, so it fits in the cache, and hopefully small amounts of instructions, so it fits in the iCache. So that's the kind of operations, the decision-making operations in the algorithm that you would allocate to the CPU. So by contrast, what the GPU is good at is very large data sets of very parallel operations. So the parallelism comes in not only from the fact that you may have wide wide word data sets, so you'll be operating on VEC4, VEC3 and VEC4 type data types, but you've also got many of these operations related to adjacent pixels, which are essentially independent data quantities, and you can stream those through the SIMD engines of the processor very efficiently. So that gives you a natural split between the functions. If you're looking at an application that you want to split between the CPU and the GPU, that gives you a natural split. It gives you a target to look at and say, okay, I've got certain operations here which have got a lot of bulk data. They're operating directly on the image. Maybe you're running a filter across an image to do an edge detect, something like that. That can go on the CPU and it can go on there very efficiently. But then I've got something a little later on. Perhaps I've extracted feature points from the image on the GPU, and then you want to go back and say, well, what do those feature points mean? Now, there's a lot of decision making which is done as a result of those, or as part of those operations. That's much more appropriate for the CPU. So that's kind of a guidance as to where you would want to split. Did I press the wrong button again? Hey, here we go. Okay. All right, so this is what we built. Okay. So inside an imaginary SoC, this is the multimedia subsystem inside an imaginary SoC built with Imagination Technologies IP blocks. So we've got, this is the camera ISP that I've been talking about. It's called Raptor. That's the architecture name for it. Then you can put in a MIPS CPU, a PowerPR, a Rogue Series 6 or Series whatever GPU compute engine, which is also your graphics engine. Then we also have the PowerPR video encoders. So in addition to those blocks, those IP blocks, there's also there's the system aspect, and this is coming back to what I said earlier on, that we're really a system company, not just an IP block company. So we've created pathways between, let's say, between the camera ISP and the video encoder, which are typically in a normal situation, the images would simply flow into DRAM, and then maybe you would pass a pointer to the image encoder, to the video encoder, and it would pick up the images and it would encode them and it would stream them out on an MPEG-2 transport stream or something like that. But memory transactions waste a lot of power. So we worked hard to reduce the number of memory transactions. So we created a path, a direct path between the Raptor ISP and the input of the video encoder to send the images directly, so that it will do the encode without going through main memory, and that gives you a much more power efficient solution. It also gives you a much more low latency solution. It doesn't allow you to use B-frames, but for video conferencing, you really want low latency. So that was the objective there. But in addition to the images, that other line there, the solid line there, that's forwarding image statistics on a frame-by-frame basis between the camera pipeline and the input of the video encoder, and it's a histogram. It's an entropy histogram of the line of macro blocks that are just to be encoded by the next line, which is to be encoded by the video encoder. And what that allows the encoder to do is it's as though it's done a two-pass encode job. What it allows that to do is it allocates its bits more appropriately for the distribution of entropy across the line, across the group of lines in the macro blocks, right? So you get, by allowing the ISP and the video encoder to collaborate in that way, you get not only a lower power solution, a more efficient encode, you get a better result because you've got better allocation of your bit rate for the particular image. And that concept is expanded, with all of the other blocks. We have the ability to put, some other vision IP. It's stated as customer's vision IP, but it could be our own. But it's a block which may be hardware, maybe a processing block. It's something where you want to do one of the vision functions that is necessary in the system, and we have the ability to create statistics and analyze the images coming through the camera IP at the very first opportunity that you have to analyze or to manipulate those images in such a way as to make it easier for the robotic vision, the computer vision block to do its job. And there are other things that we've got in there as well. We have a lossless compression scheme which allows us to save images into memory much more efficiently. All of these things are aimed at making a more efficient system, so that when you put all of these blocks together, the whole, the sum total of what you get is more than just the sum of its parts. The combination is much more powerful than using these blocks individually. So here's a couple of examples. I am not looking at a clock. How long do I have left? Sean? Sean? He's not listening. How long do I have left, Sean? 5 minutes? I'll speak. That's fine. It's just I don't have sight of a clock from here. Okay, so this is a good example of the kinds of things that you can enable by using a vision-oriented ISP in this is in a video conferencing example. So this, it's a little difficult to see, but basically this is the original image, and this is an enhanced image. So it's image beautification. You could look at it as sort of a vanity thing. And that's fine. Actually, I look at it as a processing efficiency kind of thing, because this is a very much smoothed out image, and us old wrinkly people take more bits to encode than beautiful young people, if you like. So these are the kinds of functions that you've got in order to produce this effect. And you can see that these are the kinds of functions that you'll get in an image processing library like OpenCV. And I'll give a shout out actually for OpenVX right now. This is a new standard which the Kronos body has come up with to try to specify the set of image processing algorithms and functions which can be exposed through a standardized API. To the applications. It's an important development. It's actually a recognition of the changing role of the image sensor, that now we have a standards body which thinks it's the right time to standardize the functions which are available for this kind of activity. This is another interesting one from retail analytics. If you were watching Hussein's talk earlier, he referred to a retail analytics project that we've done with someone, and this is the one that he was talking about. It's a company called Vadaro, who they do kiosks for retail. And what's going on here is the camera is just observing the scene, and it will do face detection. But it goes much further than that. As soon as it's detected a face, it extracts the characteristics of that face. It sends it up to a cloud-based analytics program, which will tell you what. Well, it'll decide what sex the person is. It'll decide approximately how old they are, and then it will subtract 10 years for all the ladies, and it will, and that's actually true. I'm not joking. It will decide what your ethnicity is, and it will do things like it'll observe whether there's someone comes up to the kiosk as a single person, or whether there's a couple, and it will take certain decisions based on that information that it's derived from the images. It'll present different products. It'll present the same products in different ways. If there are two people, it'll assume that they're together, and it'll present the kinds of things that are of interest to married couples, that sort of thing. And that's all done by analyzing the faces of the people which are standing in front of the camera. And this turns out to be an extremely important application for retail. And this is another one. It's called Find Exact, Find Similar. This is Kate Middleton. And many people are interested in wearing the same dress as she wears. The same effect happens with men. I mean, many people are interested in wearing the same tennis shoes that Kobe Bryant wears, or whatever. And so what you can do is you can take an image like that, and you can say, okay, I'm interested in this object in the image. Find everything that on the web. Go out and search for things that look like it. And so it will present you with lots and lots of examples, which you might possibly then want to buy. And so this is another retail example. This turns out to be very important because they want to sell us stuff. It's important for us too, because have you noticed how hard it is to find stuff when you go shopping these days? I mean, it used to be easy. There were only a few sites. Now it's a huge problem. So this is like Google for shopping, basically. Okay, so this is just a summary. The basic message is that the role of the image processor, the role of the imaging device, is producing pretty pictures, actually producing data that can be worked on by other applications. So it's doing that through the medium of robotic or machine vision. In order to get to the performance level we want in a handheld or a mobile or even a kiosk-mounted device, we really need to use the most efficient processing which is available to us, and that turns out to be heterogeneous processing using the GPU. In the future, it might be different devices, but right now, using the GPU in order to get the performance at the power consumption points that you want. And as a result, the ISP is moving. We no longer have ISPs separate, embedded in the CMOS sensor. That's moving on chip in order to be able to work in a collaborative computing environment. Thank you.